we're going to get started. Hopefully the last few people get here shortly. So again, today we're going to go over the last part of section 3.2, where we stopped yesterday. And then we're going to look at some examples of where these scatter plots and things kind of show up within AP exams. So I've got a couple examples from recent year AP exams that we're going to look at to see how the stuff we talked about in chapter 3 might show up, and look at those specific examples. And then we'll be done for the day, so shouldn't be too bad. Yeah, I'm still working on getting all the resources and stuff ready for chapter 3 in Canvas. Hopefully I'll have that all done shortly. And then the multiple choice assessment covering chapters 11 and 13, I'm hoping to have ready by the end of the week, and that will ultimately be due before the end of the semester. So you'll have a little bit of time to work on that, a couple weeks. All right, and yeah, so there's that. Wanted to make sure I mentioned that, and then we're going to get started. Look at this. There we go. Alrighty. So this is where we left off yesterday. We didn't actually show you the screen. This was the next one. And this is something that we're going to look at a couple of different interpretation or a couple of different representations of computer regression outputs. The important thing is to be able to identify, as this says here, the slope, y-intercept, and values of s and r squared, given these computer outputs. These are things you might see on an AP exam or other different examples. And you just need to be able to find those values so you can then say something about them, interpret them, use them to make a prediction, something like that. All right, so here we have our first example of a type of output we can have. This one is through the program called Minitab. There's other programs that produce different outputs with the same information, they're just formatted slightly different. So this is the first one. We're going to look for the slope b, the y-intercept a, and the values of s and r squared. And so in this first example here, we have predictors, coefficients, standard error coefficient, t, p. We're really only looking at these coefficients and then some values along the bottom. The constant is the y-intercept. And that's because in the equation of a line, the y-intercept is the constant value in that equation. In this case, that is a. Right? A plus bx. All right. The miles driven here, this goes along with our slope. Now this goes back to the context of the problem that we saw yesterday with the used Ford F-150, and the price of it is dependent on the miles driven. And so this is saying that per mile driven, right, the price adjusts by 0.16292. Okay, so we have this. And yeah, and that should be a negative. I'm not sure why there's not a negative on there. Then we have S, which is our standard deviation of the residuals. This is essentially how far typically each point will be away from the regression line. Then we have our R squared. In this case, is 66.4%. We don't want to look at the adjusted one. We're just looking at the normal one. And that kind of tells us how much of the time the regression line is going to be close to what we want. A good predictor, kind of. All right. And so we have our values here. And those are the only 4 values we're really concerned with at this point. Obviously, there's more values. Right. We have another output here, formatted slightly differently from a different program. And this has our summary of fit and values, and then parameter estimates. Again, we have r square, which is r squared. This format gives it to us as a decimal instead of a percentage, which we can easily convert to a percentage by moving the decimal place over 2 spots to the right. And then we have our root mean square error. That is our standard deviation of the residuals. All right, that one doesn't really have a nice correlation between the letter S and what it's saying here. So essentially, we're looking for this root of the mean square error, right? Because we can have S squared, which is the squared standard deviation. So we're taking the root of that. And that's our S, standard deviation of the residuals. On the parameter estimates, the intercept is the y-intercept, value for A. And again, we have this miles driven, which corresponds to the slope. All right, so we have the same pieces of information in this other computer output. It's just in different places. So we need to be able to identify which one is the value we need. And it's fairly common for one of these outputs to show up on an exam, so we want to make sure we've seen it. We know where to find things. Is there any questions? Anything I can clarify on the 2 different computer outputs? All right. All right, we can also find the equation of our least squares regression line using the means from our data. Now, using technology is often the most convenient way to find the equation of a least squares regression line. It is also possible to calculate the equation of the least squares regression line using only the means and standard deviations of the 2 variables and their correlation, right, the value of r. Right, so in the event that you're maybe not given the full data set, but you're given the means and standard deviations and correlation, we can use that to come up with the regression line. Right, we have data on an explanatory variable x and a response variable y for n individuals. From the data, calculate the means and standard deviations of the 2 variables and the correlation r. The least squares regression line is the line y hat equals a plus bx with slope b equaling r times s sub y divided by s sub x. It's kind of like r times rise over run. We have a standard deviation of y divided by standard deviation of x. And y-intercept A equals y hat minus b times x, or not y hat, y bar. The mean minus b times x bar, which is the mean of x. Right, so we need b before we can find a, because we use b here. Okay. So we can calculate this. Typically, you'll be able to get this value, you'll be able to get the linear regression line, the least squares regression line, if you have the data set. You'll put that in your calculator, list 1, list 2, and have the calculator do that for you. You'll get all the necessary values that way. Does anyone need a moment to write anything down from this screen? Correlation and regression wisdom. Correlation and regression are powerful tools for describing the relationship between 2 variables. When you use these tools, be aware of their limitations. The distinction between explanatory and response variables is important in regression. All right. We have this example again, the miles driven versus price. We have our data set, we have our scatter plot, we have our least squares regression line. We have the equation for that line, the value of S, standard deviation, and R squared, based on miles driven being the explanatory variable and price being the response variable. All right. Remember, least squares regression lines makes the distances of the data points from the line small only in the y direction. That's what we're concerned about because that's a response variable. Right. If we reverse the roles of the two variables, we get a different least squares regression line. Which you see here. If we swap these and now put price on X and miles driven on Y, we obviously get a different scenario. Right. The regression line is a little more steep. Right. And S is now looking at the, right, our standard deviation is still using Y, which is now miles driven. So that S value is much larger than it was for the other data set, or from the same data set in the other way. Right? We notice R squared is the same, 66.4% for both. All right, and that's because even if we switch X and Y, this has no effect on the value of R. So again, R and R squared aren't going to be affected if you graph this or have your calculator use the wrong list in the wrong spot. You will end up with the wrong linear regression equation, right? And this will then in turn cause you to have the wrong standard deviation of the residuals. That could be a problem. Right, so it's important to know which one is actually the explanatory and which one is the response, and that they go in the right spots. So anything I can clarify about that? Okay. So now, the second thing here, correlation and regression lines describe only linear relationships. All right, we can see we have 4 different graphs here representing 4 different sets of data. All right, some of these are obviously not linear. So I want to do a quick poll of the class here. For these 4 graphs, these 4 scatter plots, which one do you think has the highest correlation? Which one has the largest value of R? Right. So if you think A, right, scatterplot A has the largest value of R, please raise your hand. Digitally raise your hand. There's no risk for being right or wrong here. It's just guessing. If you think B will have the largest value of R, the highest correlation, raise your hand. All right, what about C? And what about D? It looks like everyone thinks that C will have the highest correlation. It seems reasonable. It's the one that looks the most like a straight line. But here's the rub. They all have exactly the same correlation. All 4 of these graphs have an R equal to 0.816. All right. So essentially what this means is we can calculate a correlation for any scatter plot. That doesn't necessarily mean that the correlation and then a linear regression is appropriate. Right? It's kind of obvious to see that for like graph B, a linear model is not appropriate. That is obviously a curve. So using a line to represent that relationship wouldn't be correct. Again, in graph D, right, that's like a could model that with a line, but that's a vertical line going up and down, which doesn't really fit into the type of correlation R, or a linear regression, that we're using here. Right? A and C are more linear than the other two. Right? We can only use these values, correlation and linear regression, when we have something that looks linear, something that can be described well or modeled well with a linear regression or line. Okay, but again, we can calculate these values for any scatter plot. Right? I can find a linear regression for all four of these graphs, and they actually all four have the same linear regression. Does not mean it's a good model. Again, for graph D, if we use that linear regression, y hat equals 3 plus 0.5x, it's not going to be appropriate most of the time. It's definitely not going to find values that we expect based on a majority of the rest of the values. So again, the main point is the correlation and regression lines are only for linear relationships. So you have to be mindful of that. Is there any clarification I can provide on this? And then number 3 here, correlation and least squares regression lines are not resistant, meaning they're not resistant to outliers. Right? We already learned in 3.1 that correlation, R, is not resistant to outliers, mainly because it uses mean and standard deviation to be calculated, and mean and standard deviation are not resistant to outliers. Right? One unusual point in a scatter plot can greatly change the value of R. The least squares regression line is also not resistant, and the graph shows how outliers can change the line. So here's the original data set with a regression line running through it. We can see outliers of child 19 and child 18. 19 is basically far away from our regression line here, and 18 is an outlier because it's far away from the main cluster. If we remove either of these 2 points, the line changes. Value of R changes and the regression line changes. Right, and we can see the different lines that occur if we remove child 19 or if we remove child 18, and the different values of R and Y hat that occur. Okay. So again, these outliers can have a great effect on our regression line and the value of R. Least squares lines make the sum of the squares of the vertical distances up and down to the point as small as possible. That's the goal of the line. A point that is extreme in the x direction with no other points near it pulls the line towards itself. We call such points influential. Right, and so this is saying a point that is extreme in the x direction, no other points near it pulls the line towards itself. We actually see that here. Right, we have our outlier of child 18 pulls these regression lines towards it. When that point is removed, There's a huge adjustment to the regression line. An outlier is an observation that lies outside the overall pattern of the other observations. Points that are outliers in the y direction, but not the x direction of a scatter plot have large residuals. Other outliers may not have large residuals. And that kind of makes sense. An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. As we saw in the previous example that I went back to, right? That child 18 is a more influential point in that it swings that regression line. Right? Points that are outliers in the y direction have more of an impact on residuals. We need a moment to write anything down from this screen. And that actually brings us to the end of the presentation for section 3.2. In this section, we saw how to interpret the slope and y-intercept of the least squares regression line, use the least squares regression line to predict y for a given x, calculate and interpret residuals and their standard deviation, explain the concept of least squares, determine the equation of a least squares regression line using a variety of methods, construct and interpret residual plots to assess whether a linear model is appropriate, assess how well the least squares regression line models the relationship between two variables, and describe how the slope, y-intercept, standard deviation of the residuals in R-squared are influenced by outliers. Right, and that's the section in a nutshell. So we're going to stop that. And now we're going to look at some examples, and I'm hoping my technology wants to work with this, because it didn't want to first period. So, where's my doodad? All right, this seems to be working. All right. Cool. Now if I can do this, it'll make my life easier. Oh, I don't have a lot of space there. Okay. That's fine. All righty. Cool. So we're going to look at this example here. And this is actually an example from the 2018 AP Stats exam. Go away. Thank you. All right. So in this example here, we have a manager of a grocery store that selected a random sample of 11 customers to investigate the relationship between the number of customers in a checkout line and the time to finish checkout. As soon as the selected customer entered the end of a checkout line, data was collected on the number of customers in line who were in front of the selected customer and the time in seconds until the selected customer was finished with the checkout. Data are shown in the following scatter plot, along with the corresponding least squares regression line and computer output. All right, so here we have our data. Similar to what we saw on PowerPoint, right? We have the constant, right, which is A, right? This customer's in line is our slope B. Right, so each customer in line, it basically represents 174.4 seconds of time in the checkout. So for each customer in line, that's how much more time you have to wait. Right, we then have S. Right, the standard deviation of the residuals and R squared. Right. So we have all of our values here that we saw previously, and we're going to use them. So, got some questions here. Question A, identify and interpret in context the estimate of the intercept for the least squares regression line. All right, so we've already identified it. It's right here, 72.95. So what does it mean? Right? It essentially means if there are no customers ahead of you. I can't write today. We'll wait about 73 seconds. Right? So again, that's what that says. If there are 0 customers ahead of you, it's going to take about 73 seconds to check out. B, identify and interpret in context the coefficient of determination R squared. It's a fancy way for R squared to be said. Well, we want to interpret this one. That's fine. Right? So we have R squared is 73.33%. Right? And again, that's just right here in our table, in our printout. Right? And essentially what that is telling us, because of the limited space, I'm not going to try to write all this. This value, the 73.33%, kind of represents, it indicates that 73.33% of the variability in the times it takes customers to finish checkout, including the time waiting in line, can be explained by knowing how many customers are in the line in front of the selected customer. It's essentially stating the probability of this thing being accurate, give or take. Okay, 73.33% of outcomes can be represented with this regression line, and it fairly accurately accounts for how much time you would have to wait given the number of customers. Okay. And then one of the data points was determined to be an outlier. Circle the point on the scatter plot and explain why the point is considered an outlier. All right. The outlier is going to be this point right here. It is very far away from our regression line in the Y direction, but also in the x direction. It's just far away. Okay. More related to the context, this is essentially showing a huge difference between the expected time to checkout compared to the number of customers. We would expect that time to be much higher if there's 3 customers ahead of you in line. So it doesn't fit the overall pattern. Alexis. All right. Are there any questions? Is there anything I can clarify on this example? Right, now, this example doesn't start with scatter plot, but that's okay. Okay. All right, it starts with our box plots. We'll get to the scatter plots in a moment. Okay. So this right here represents attendance at games for a certain baseball team, and they're being investigated by the team auditor. The following box plots summarize the attendance measured as excuse me, average number of attendees per game. For 47 years of the team's existence, the box plots include the 30 years of games played in the old stadium and 17 years played in the new stadium. So we have our 2 box plots. This is, we could have been drawn this way and stacked like that. They chose to do it vertically, and so we have something that looks like this. Right, we want to compare the distributions of average attendance between the old and new stadiums. Yes, and this is actually one of the released problems from the first administration of the AP Stats exam this year. So this is very fresh. Okay, so we want to compare these 2 things. When we're comparing 2 distributions, 2 quantitative distributions, we want to look at shape, center, and spread. How do their shapes compare? How do their centers compare? How spread out are they compared to each other? Right. So if we look at these 2, our old stadium looks fairly symmetric, right? We have the center is kind of in the center of the distribution. We would assume, or we would guess, that maybe the distribution would look something like that. Fairly symmetric. We're not going to say it's normal because we don't know enough to say that. We're just going to say it's symmetric. Compared to the new stadium data that is much more spread out, that we would expect maybe to look more like this, right? Which would be more skewed. It does have a tail to the right. Well, actually, that would be left skewed if we were to draw it horizontally because of the way their data is going. Either way, that's not very important to the comparison. We can essentially say that the data for the old stadium is fairly symmetric as opposed to the new stadium, which is skewed, right? Possibly skewed to the left. The distribution for the old stadium has a smaller center if we're looking essentially at the IQR compared to the new stadium. And the old stadium has more variability or less variability compared to the new stadium. Neither of these distributions has outliers that have been identified in this graph. And that's the comparison. We're not making any conclusion about these things. We're just stating how they're the same, how they're different. And that's it. Now we got a scatter plot. The following scatter plot shows average attendance versus year. We got our years along the bottom here. We're actually showing the difference between old stadium and new stadium using different points. We got our average attendance in thousands. We want to compare the trends in average attendance over time between the old and new stadium. If we were to just imagine where these lines might be for a best fit line, right, we would have maybe for the old stadium, maybe something like that, versus the new stadium, right, which is going to be a bit more steep. Right? We're not obviously calculating these things right now. We're just guessing and kind of drawing a best fit line just to get an idea. Right? So when we're comparing the trends, right, in both stadiums, average attendance has a positive linear relationship. We can say that because both of the lines that we have here have a positive slope. They have a positive association. And they both can be modeled decently well with a linear model. Right? The old stadium shows a slower increase in attendance over time. Right? Has a smaller slope. All right, compared to the new stadium. And that's really all that we can say at this point. We don't have more data to use yet. So that's our comparison. So anything I can clarify on this example? This part. All right, so now we have two more scatter plots. Graph 1 and graph 2. Graph 1 shows the average attendance versus the number of games won for each year. Right? There is no differentiation between old and new stadium. Describe the relationship between the variables. Okay. And again, if we wanted to, we can kind of visualize or just sketch a best fit line. Whether it's super accurate or not, who's to say? We'd have to put in all the data and determine that, but looks okay, right? And so when we're describing the relationship, we'll say there is a strong, right? Strong because a lot of the points are very close to the line that we drew. Positive, we have a positive association. The line is increasing from left to right. Linear relationship, because we can model it with a line, between the number of games won and the average attendance. And that's it. We don't really need to say any more about that. We've covered those three main things, right? The strength, whether it's positive or negative, and the shape, so to say, that whether it's linear or curved or something to that effect. We cover those things. That's what we need to describe the relationship on a scatter plot. So we have a strong positive linear relationship between number of games won and average attendance. Okay. Graph 2 shows the same information as graph 1, right, but also indicates the old and new stadiums. Does graph 2 suggest that the rate at which attendance changes as number of games won increases is different in the new stadium compared to the old stadium? Explain your reasoning. Now, if we look at the line we drew for graph 1, obviously it's going to have the same best fit line for graph 2. So just based on that, it looks like the trend, regardless of stadium, is the same. More games won seems to result in higher attendance. We don't know if that's a causation. We just have an association there. All right. Leave that there, actually. So we're trying to say, does the stadium have any effect on this? Really, no, there's not. The slope of the least squares regression line for the number of games won and average attendance for the old and new stadiums is about the same. We might, if we drew two separate lines, get slightly different lines for both data sets, but not that different. So this means that the rate at which attendance changes as number of games won increases is about the same between the two stadiums. So lastly, last question they want us to consider. If we're considering the three variables, number of games won, year, and stadium, based on the graphs, explain how one of those variables could be a confounding variable in the relationship between average attendance and the other variables. So the average attendance related to the year, average attendance related to the stadium, average attendance related to the games won. Which one could be a confounding variable to the other two? All right. Essentially, in this case, games won could be the confounding variable, because when we're trying to find a relationship between the year and attendance, right? If they won more games that year, that could be the explanation over the year, right? If they won more games, people are going to attend more. And then versus old and new stadium, right? When they switch to the new stadium, they may have won more games because the players were more motivated to be in a new stadium, right? And it might not, the new stadium might not be the cause of the attendance. It might be because of the wins. So the wins, games won, is essentially the confounding variable in this case, because it kind of worms its way into affecting the data for both other cases. And in this, you should really be able to make an argument for whichever one you choose, right? So if you have a strong enough argument, your answer could be considered correct. All right. So those are the examples that I wanted to show today as far as scatterplots, and those are two examples from recent AP exams, right? This year's first administration of the AP exam and the 2018 exam. So that's why I wanted to make sure we covered chapter 3, right? And the printout, because those things show up. Are there any questions? Is there anything I can clarify? All right. Okay, so next week we'll be doing more AP prep, AP exam prep, go through other examples. We're specifically going to be focusing on FRQ questions, the free response questions, and looking at the questions and also the grading rubrics that have been used in previous exams, so we can get a better feel and better idea of what graders are looking for, what things need to be included when you're writing your answers and things like that. So that'll be next week. And other than that, that's all that we have today. Be on the lookout for the other resources and the last multiple choice assessment. Have a great rest of your day, and I will see you all next week.